Okay, I will get better at this. I'm actually setting a timer on my phone now. My camera here will take 15-minute videos. So I forgot to set a timer the first time. So, sorry, part 2 got cut off, and then part 3 is going to be really short. This will be part 4. Let's continue. So we talked about our heat engine here. Cyclic heat engine. Now, again, the purpose of a heat engine, is to get this heat. We want to put this heat in and get this work out. That's what we want. So if we look and consider the efficiency of this engine, what we want is going to be this net work out, the difference between the work out and the work in. To get it, we're going to have to put heat in. So that's going to be our numerator and denominator for our efficiency expression. What we want divided by what we desire, what we're after. Now, notice from the previous slide we said this net work out is equal to, which the net work out is the difference between the work out and the work in. The net work out is equal to heat in minus heat out. So if I plug that in here, the net work out is equal to, just goes the paper here. Right. We said our efficiency is going to be what we want, the work we get out of this thing, divided by the heat we have to put into it. Now, since we said that the first law for the heat engine yields this. The difference between the work in and the work out is equal to the difference between the heat in and the heat out. And so if I plug that in here and I massage this equation just a little bit, right? So I'm going to plug this in here. This is going to be Q in minus Q out divided by Q in. So do that pretty quickly. That's pretty basic algebra there. Break up the top fraction. So the efficiency, which again, what you want, divided by what you have to do to get it. It's always true for an efficiency. It's also equal to 1 minus this ratio of heat transfers, Q out over Q in. This portion is going to become more important as we get a little bit later here. This one's always true, the first one. But the second one is a little more specialized for a heat engine. Okay. All right, now to continue on with what I would normally do in class, my normal PowerPoint slides. What we normally, well, especially in this textbook, I've seen it in some other textbooks, but this textbook really likes to apply H and L subscripts to the high temperature source, H for high temperature source, L for low temperature source. Right? So if we go back over here, and I've done that a little bit here. I said this is TH and this is TL, the low temperature sink. And so they've got a very basic, simple example here where they're saying, let's keep the numbers simple. Right? Let's put in 100 megajoules into this engine. Let's say we generate 55 megajoules of work as a result, and we can't turn all of that 100 megajoules into work. Some of it's got to go somewhere else, so we're going to reject the remaining 45 megajoules somewhere, to the atmosphere, somewhere like that. If we look at the efficiency, I can put 55 over 100, and that gives me 55%. The same way I can take 1 minus 45, this 45 divided by this 100, and still get 55%. So that's real simple, really, really simple example. We can do that math in our head, most likely. But the big thing here is the subscripts of H and L. Notice they've applied those. They're not saying heat in and heat out. They're saying this is the heat from the high temperature source and the heat to the low temperature source. And that's something we will do throughout this chapter is using those subscripts. H to represent from the high side, the high temperature side, L to represent from the low temperature side, and that's going to be helpful when we talk about refrigeration cycles in just a little bit. Right, so the heat in is coming from the high temperature side. This is 1 minus the heat to the low temperature side divided by the heat in from the high temperature side. And that's normally how we will write these. Okay? Now, at least moving forward, that's probably how I'll write them. When I'm talking about heat, I will avoid using in and out. I'll refer to it as a high temperature source or the low temperature source. Okay, recall our good friend Klaus has told us that it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a lower temperature body to a higher temperature body. That can't be the only thing it does. Now, when I first introduced this, I said, remember though, there are devices that actually cool your cool substances for us. We have air conditioners and we have refrigerators. Those are devices that actually remove heat and move it to another location. So Klaus's is not saying you can't do it. That just can't be the only thing you're doing. Refrigeration cycles, a refrigerator is actually a device that transfers heat from a low temperature medium to a higher temperature medium. To do it, because Klaus's says that can't be the only thing you do, to do it requires some work input. Now, we mentioned working fluid for engines. The working fluid for a refrigeration cycle we call a refrigerant. We've talked about refrigerant 134, R134. I forget the organic chemistry name for it off the top of my head. You can look it up. We use refrigerants. That's refrigerant 134A we use as a common refrigerant because it will go through a phase change at a very convenient pressure temperature mixture for us. And it tends to operate very well in a refrigeration device. Ammonia tends to do very well. In fact, it's very efficient. Ammonia-operated refrigerators tend to be very efficient. Problem is the ammonia is quite toxic, very toxic to people. So it's when we put a refrigeration device in a residential setting, like your refrigerator in your kitchen or the air conditioning, the refrigerant that's in your air conditioning unit, we assume that that's going to leak out at some point. That's just what those devices are going to do. Over time, that stuff will leak out. If it's ammonia, that's toxic. That's really not good. The other stuff, you don't want to breathe it in. If you spring a leak, you evacuate the area and get it ventilated, but it's not like ammonia where it's guaranteed to kill you. Refrigerant's just not good stuff. I'm not saying go breathe that in. It's just not as toxic. So, at any rate, refrigerants, those are just substances that we use as a working fluid within a refrigeration cycle. They go through a temperature, at a convenient pressure temperature mixture, they go through a phase change for us. And just like I did with the heat engine, I'm going to draw this out with you guys. I've got about 6 minutes or so before my camera cuts me off. Let me start with a new sheet of paper here. Let's draw out the refrigeration cycle. Let's talk about how a refrigerator works. So a refrigerator is going to have about the only thing that's got moving parts is the compressor. And I like to draw a turbo compressor, the opposite of a turbine. Compressor is a device that requires a work input. Now what the compressor is going to do in your refrigerator is it's going to increase the pressure of the refrigerant. Now, if you think about if you squeeze a gas, if you squeeze a vapor, what happens to the temperature? Well, if you look at ideal gas law, it's going to tell you that the temperature is going to increase. The goal of a compressor in a refrigerator is to get the temperature of the refrigerant so hot. You want it screaming hot. You want it so high temperature that when you run it through a heat exchanger, that it is actually hotter than the high temperature medium. So it will actually, the refrigerant will actually lose heat to the high temp reservoir, TH. So the goal of the compressor is to get the refrigerant so hot that it will actually lose heat to the high temperature medium. So it's going to come out, it's still going to come out high pressure, but it's going to come out, we'll say, I like to say medium temperature. Now we're going to run that through a device that is kind of magic. What we call an expansion valve. Now I'm not going to talk about supersonic flow in here, but interesting things happen when you achieve supersonic flow. And one of the neat things that happens is the temperature drops if you allow the substance to expand. And that's essentially what happens here. The best way I know to explain this is think about if you take a can of some kind of aerosol, so like the compressed air that you use to clean electronics, and if you hold that can open for a long period of time, what happens? Have you done that? You watched a video of that? Don't do this on your own unless you're wearing gloves and very careful. If you take that high pressure contents of that can, you hold that valve open for a long period of time, eventually the temperature drops. You start getting really cold fluid coming out of that thing. If you turn it upside down, you'll start spewing this really ice cold liquid. Don't do that. That really don't put it on skin. And don't touch that with the skin. That's really bad stuff. But that's basically what's happening here. Is you're taking a high pressure, you're going to allow it to expand to a low pressure, and in that process, the temperature is also going to drop. In fact, it's going to get so cold. You allow that substance, that refrigerant, to expand. It'll get so cold that when you put it in another heat exchanger, the goal is to get that refrigerant colder than the temperature in the cold space. Spelling's not my strong suit today, sorry. I don't know if it ever is. Anyway, so you got your cold space at low temperature. The goal of the expansion valve is to get the temperature, allow the substance to expand so it drops in temperature, get it so cold that it will actually absorb heat from the cold space when you run it through what we call the evaporator. If you've ever taken apart a refrigerator, or if you've looked inside, like if you change filters out in an air conditioner unit, and you see these fins, these aluminum fins. Right, well, there's aluminum fins on the outside for the condenser. That's what's losing heat, the side that's hot. That's the outside portion of your air conditioning unit. The evaporator you may not see unless you actually really dig in and look. Those are aluminum fins inside, and they are cold. That's because you're running this low temperature refrigerant through those coils, and it's so cold that it'll actually absorb heat from this low temperature source. And then this substance is ready to go back in. This is low pressure. It's we'll say low-ish temperature. It's not really a word, but we'll say that's going to be low pressure, low-ish temperature. It's heated up a little bit, and we want to run vapor back into the compressor. Why vapor? Well, we're going to compress it, and liquids don't compress. Right? That's actually bad. You don't want to run liquid into your compressor. And if you ever lay a refrigerator over on its side, you're supposed to let it stand up for a long period of time because you want all that liquid to drop back down into the low pressure side, if you will, and because you want only the vapor to get up into the compressor. And if the compressor senses, most of the time you got a sensor in here somewhere that if it senses any liquid whatsoever in the refrigerant stream, it'll shut that compressor off. That tells it, oh, the temperature of the cold space has dropped enough that it can no longer heat it up to generate vapor, so it's time to stop. And with that is time to stop my videos because I'm approaching 15 minutes. So I'm gonna hit her pop here. We're gonna restart in just a second.